Assalamu alaikum warahmatullah. So, good afternoon, I think. So, today we are going to discuss about the reference dosimetry for high energy electron in water. So, basically, when you do calibration, when you do the reference dosimetry in water for electrons, there are few things as we have discussed in the previous presentations when we are discussing about the photon reference dosimetry. There are also same type of recommendation when you select the chamber for absolute dose, basically not absolute, it's a reference dosimetry. So there are few recommendation which is actually I highlighted here. What is the best chamber you should be using it, and they are the detailed description in the TRS 277 and 381 and IC 60731 standard. They talk about what is the cavity, how it should be, what is the diameter of it, what is the collecting electrode diameters, cavity height, between, how much the height between the two electrodes. Um, Collecting electrode should be surrounded by the guarded ring. What do you mean by guarded ring? If anyone has anything, this is the questions normally examiner asks you in the interviews. What is a guarded ring for the electron chambers? It's a very beautifully explained in TRS 27381, I think. Just it's like a one paragraph, but it's really very good information, and there are some detailed description is given in TRS 398, which actually what it do actually it's control the electron fluence basically. So if you read through and if anyone has any questions, send it to me. I will explain you. There's a beautiful presentation on YouTube as well, so you can have a look if you want. So there's a recommendation for the thickness of the window. The front window should be restricted to 0.1 gram per centimeter cube or 1 millimeter of PMMA. Construction should be more homogeneous, and air cavities shouldn't be sealed, as we have talked about in the farmer chambers. It should be vented chamber, as we have the for the reference dosimetry. QR. I need it. Okay, so there are two ways to have a reference dosimetry for electrons. One is called the direct chamber. If the chamber is directly calibrated for cobalt 60, if you send your plain parallel chamber or the farmer chamber, and you get the reference, the calibration certificate, and you get the calibration factors for your chamber for cobalt 60, and you can use directly for your reference dosimetry for electrons. It is recommended in TRS 398. Not recommended, is the provision is available. You can use it, but there are some issues. I have actually at the end of my presentation, I have just put to it today. I put some summary of it, so I hope it will help you. So we will discuss in the last last part of the presentation. And the another one is called the cross-calibrated chamber. For example, you get your farmer chamber calibrated for cobalt 60 and from the SSDL RPSDL lab, and then you cross-calibrate your parallel plate chamber for your electron dosimetry. So if you don't mind, just give me a second. I just quickly close the door. Can you close the door, please? Yeah, so sorry. So there are, the third option is also available, which the third option is actually your chamber is directly calibrated for your electron beams. Just like we have for photons, we discussed in the in my presentation, we have discussed the direct beam calibration. But the problem is the availability of the direct beam calibration is very, very, very limited, and it's not easy to do the direct beam calibration. There's a lots of issues with that. Actually, I don't want to go in that details, but if anyone's have any concern, interest, let me know so we can discuss. You can email me, and I will give you a feedback about that. Normally the recommendation is it should be used the plain parallel chamber. This is what the recommendation from the TRS 398. They recommend you can use the farmer chamber, but up to 4 gram. If your R50 is greater than 4, you can use your chamber, plain farmer chamber. But if you have to have make sure that your beam energy, your R50 of your beam is more than 4 gram per centimeter cube square, for more than 4 centimeter R50. But if you're using the plain parallel chamber, it you can go up to 0.1 of 1, I think. So 1 gram per centimeter square. So the your R50 could be up to 1 centimeter. So these are the detailed description, bit of informations about the guard ring and your A cavity, the distance and collecting electrodes and effective point of measurements and details. So in the reference dosimetry, the setup is very important, as we have discussed in the in the photon dosimetry. The same sort of setup. I have a question in the last presentation about why we using 10 by 10 for our absolute for the reference dosimetry in electrons and photons. I think so. I was saying in a comment section, but no one has actually answered. I think maybe I missed it. If someone answered, I'm sorry for that. But 10 by 10, normally we use it because our chamber is calibrated at 10 by 10 field size from the PSDL or SSDL lab. So that's why if you use the bigger field size, there is an issue with the with called the stem effect of the chamber. So because your chamber is not exposed, the exposure of the chamber is more than what you're exposing in the, if you increase the field size, and your wire will be more in the field size. So that's what is important, because whatever your chamber is calibrated for the field size in the primary standard or the secondary standard, you should be using the same field size for your reference dosimetry. That's why there's some issues with the, if you TG481, which is small field dosimetry, there are some ways to deal with that. They have talked about this one, so intermediate and things like that. So effective point of measurements is for plain parallel chamber. In the previous slide I showed you, it's the, the front window of the chamber. You see the front window? The front window, this bit is actually here. You can see it here. This is your effective point of measurement. But anyway, I will explain you in the details in the further slides. The cone size for R50, which is a critical, when you're measuring your R50, normally you do your percentage depth ionization. So it is recommended to use the 20 by 20 or greater if your R50 is greater than 7 gram per centimeter square. And the applicator size could be used 10 by 10 if R50 less than 7 gram per centimeter square. There is a beautiful description has been explained in TRS 398. I recommend you to read it, but I will just give you a brief information about that. So basically what it do actually, when you doing a smaller field, and they recommend you can use your 10 by 10 applicators for higher R50s, but you want to make sure that your R50 not change between, if you do 20 by 20 applicator and 10 by 10 applicator, your R50 didn't change much. It's 0.1 gram per centimeter square. So, which is not easy, because the problem is the scatter conditions will be changed a lot. Because as you know, the more smaller the cutout, Okay, one more thing is, if anyone has studied the output factor for electrons, if you studied the electrons output factors, you will see how it will change as you change your field size. Then you will understand what is happening there. So it is actually the scatter conditions from the applicators itself, so which can contribute to the central axis a lot when you are doing a PDDs or percentage depth ionization curves. So there is cone size is recommended is 20 by 20 for measurement for R50 using cylindrical chamber. You If you're using a plane parallel chamber or thimble chamber, so you have to make sure that you get percentage depth ionization curve, and then you have to convert it to percentage depth dose to get your R50. If you don't have in your software, you can't do it R50, then you can use R50 ion, and there is a two equation which is here, um, they have actually explained. Uh, you can use this equation. Do you know why you have to use this equation if you're using R50 to R50 ion to convert it to R50? So this is the one of the common question in the exams they will ask you. Okay, another question they normally ask you in the exams, if you are doing with the diodes, if you're measuring, I talk about plane parallel chamber and the thimble chamber, but if you're doing with the diodes, do you have to correct for your whatever you get it is a p your percentage depth either ionization curve, or you get the percentage depth dose curve. So this is the same question I have asked in the presentation and the last presentation. I think the answer is in this presentation. I have actually explained it in the next slide. So there's another question. They ask you the ZREF, the position, give you the okay. So yeah, ZREF. What is the ZREF? ZREF is the position is not the Dmax position of the energy. So when you do your measurement, you don't measuring your output at the Dmax of the energy. So you are measuring at a depth which is pretty close to the Dmax, specifically with a low energy. But when the high energy goes, it's significantly different from your Dmax. Okay. And do you know why we have to do it as ZRAF? There is a detailed information actually in TRS 398 if you read through chapter number 7, I think, which is electron dosimetry. Um, I I'm giving you a hands up. I'm not giving you all the answer. The reason is behind it because you have to go and read it. If I tell you now, you will forget in few days. But if you go through and open the book and read it, you never forget. So there are a few things about the reference setup. The highest electron beam energy should be must be high enough to make the okay. So this is basically a TRS 39, which is talk about the uh, P replacement perturbation. The perturbation factors. So another one is the field size at the phantom surface at the 10 by 10 is R50 less than this, and your E naught energy should be approximately equal or less than 16 MeV, and at least 20 by 20 for R50 if it is greater than that. That's what we have explained in the in the setup in the last slide. So some of the accelerator at the high electron energies has an intrinsic poor homogeneity at the large field, which I actually explained about why we should have to be used 20 by 20 applicators to get your R50. So that's what the main reason, which may improve at the smaller field size as the result of electrons scattered from the collimators, or applicator cone, or etc. This is basically explained in TRC 98, which I was saying to you, just go and read through. I think so, just read through. There's a bit of more information there. I just writing the summary here. the field size smaller than 20 by 20 may be used, which I have actually talked about. That R50 doesn't change more than 1 gram per centimeter square for the value of measured TP R50 by using 20 by 20 cone. I mean to say, if you're using 20 by 20 cone, you get your R50, and doing a 10 by 10 and you get your R50. It shouldn't be more than 0.1 gram per centimeter square difference between these two measurements. Your R50 should be pretty close to each other, which is not more than 0.1 of gram per centimeter square. So this is the effective point of measurements. So if you have cut the chamber like this, so you can see this is the maximum difference between the electrodes, and this is the connecting. So this is the effective point measurement, which is inside inner surface of the front window. So which is like that. If this is the front window, if you see this bit is the front, this is the front window. The beam is coming from here. Okay, this edge where this is the end of the front window is actually called your effective point of measurements. So if effective point of measurement for the pharma chamber I already discussed about, there is a slight difference here, which is about the cylindrical chamber for electrons and the photons. I think so I have discussed about this one, which is we just discussed the effective point of measurement for the photon is 0.6 of our cylinder, but for electrons 0.5 of our cylinder. And study of the effective point of measurement in an ion chamber in electron beam by Monte Carlo simulation. They have studied by Rogers and Wong. So they have actually discussed on how it's changed with the if you have using the Monte Carlo calculation and measured. So and then they have actually did the ideal curve where it should be ideal curve for that. So what next is that the measurement using the cylindrical chamber for R50. So what do you do actually? This is the standard setting. So you do the PTDs using the ionization chamber, and then you correct your effective point of measurements. And then if you're doing a diodes, so diode is also the similar way. So effective point of measurement in diode is also be important. So this in electrons, okay, one more interesting thing which should be you are aware of that when all the electrode diodes which you use for electron dosimetry, they are the shielded diodes. They have a shielding on the top of it. That's why they sometimes they recommend you can use the electron diodes for small field dosimetry to avoid what you call is actually low energy spectrum of the beam. So, and the effective point of measurement is here, which is normally sometimes you have a lines on it and sometimes you don't have it. They give you, the manufacturer give you, or you have to do a X-ray of the diode and see where the sensitive volume is, or you can do a multiple measurement and compare your measurement with the plane parallel chamber, and then you find your effective point of measurements. And there's a beautiful papers, I forget the name of the authors, they have actually talked about how you can find the effective point of measurement, and they did some Monte Carlo calculation and also did the experimental measurements, and they found they make an empirical formula for different chambers, and they show you how you can find the effective point of measurements. And this is basically related to the chamber commissioning and how you want to, when you're doing a chamber commissioning, it's a part of it actually should be. Sorry, I have to pause it for a second. Sorry, mate. When you're doing with the plane parallel chambers, so this is the same thing which is, you have to do the effective point of measurements, which is actually the below the front window. um, when why we need to correct the percentage depth ionization curve to percentage depth dose for ionization chamber, not for diodes. It is this is the main reason for it actually. If you see the stopping power ratio, because your chamber have the cavity, and it, stopping power ratio water to air is significantly change as you change your depth. You can see here in electrons on the left hand side, this is electron one. And you can see for especially as the energy goes smaller, that the things are get more steeper, and the gradient will be quite significant for like very low energy 5 and 3 and 7. So that's why stopping power ratio is a big issue in the electron dosimetry. But if you see on the photon side, you can't see in the initial first, uh, especially with the region which we normally use it is around 10 MV to up to 20 MV. So you can see the first 10 centimeter, you can see there's a stopping ratio, stopping power, the stopping power is actually changing. But as you go further deeper, you can't see much change in it. That's why they have TRS-398 says you can use TPR 2010 to get your beam quality for photon dosimetry. But in electrons, that's because it's changed so significantly, so rapidly. So then you can't use your percentage depth ionization curve to as a PTD. But for photons, you can use it because it's not affecting too much on your beam quality. Because normally the beam quality is defined at 10 centimeter depth, and you can see the 10 centimeter depth is actually is reasonably okay here. It's pretty flat in this region, but as you go for the higher energy, like a 30 MeV, 30 MV or 40 or 50 MV, the 10 centimeter is not, is the stopping power ratio is changing. So, but in electrons, you can see on the left hand side, electrons is really, really significant. A small cavity effect can be change your PTDs shift a lot. So that's why it's recommended when you're doing your percentage depth ionization curve by using the by using the ionization chamber, you should correct for stopping power ratio. But if you are using for like a diodes, you don't have to correct it, because the diode is they said is approximately equivalent, very close to there, because there is no cavity in the diodes. They have actually silicon, and the silicon the okay, so they I think so in my this is the beautiful on YouTube, this is the beautiful presentation that someone has actually explained in details. I think so if you go and watch it, it's just like a 5 minutes video, but it explained really, really fantastic way that how it why you don't have to correct when you're using the diodes for your stopping power ratio. You know, your percentage depth ionization curve, you don't need to correct it for photon, but for you need to correct for electrons. But if you're using diode, you don't have to correct it for anything, either electron or photon. So for what I'm saying, if you use the ionization chamber, you have to convert your percentage depth ionization to percentage depth dose for electrons. But if you're using a diode, you don't have to correct it. And it is beautifully explained in this presentation. And if you want to read a bit more about this, this is quite good calibration of photon and electrons beams. This is a good paper by the Andrew. Um, so ZREF is, I asked you this question in the previous slide, why is the ZREF is recommended? So it is recognized that this choice of the reference depth may less convenient than the recommended in reference TRS 277. Since for the given accelerator, no two reference beam will have the same reference depth. However, the new depth has been shown significantly to reduce the machine-to-machine variation in the chamber calibration factors. This is a good paper by Bonds. If you read through, it will give you a bit of details how it's, you know. and the accuracy gain justifies its use. That's why they said if you use it, you will be get a more precise result, and as compared to using the Bmax. And particularly if you're using a parallel plate chamber, especially in TRS-398. By going to this depth, the protocol can make use of the stopping power ratio, which accounts for the realistic nature of the electron beam rather than the assume they are non-energetic, monoenergetic, but they're normally not a monoenergetic, and at the same time no longer require stopping power ratio tabulated as the function of the depth and R50. Because if you're using a TG51 or TRS-398, you can use the percentage depth ionization, and you can convert your percentage depth ionization to percentage depth dose by use to get your R50. No, sorry. If you're using, if there is a beautiful there is a reference in the one of my slide I've discussed in the past when we're discussing about the setup. I think here you can convert your percentage depth ionization by using R50. If your energy R50 is less than 10, you can use this formula, and if it are more than 10, you can use the formula in the blue color. So it will, you get your percentage depth ionization for R50 percentage depth dose curve and get the R50 from there and put the value here, and it will convert your percentage depth ionization curve to percentage depth dose R50. So it will give you the how you want to convert back to the, okay. So, and then for, you get your R50 from there, and then you put R50 in this formula, which is here on the bottom of this present in this slide. So you can put your R50 here, and you get your ZREF for each particular energy. For each energy has a different ZREF. So, and then your, because when your chamber is calibrated to the reference chamber, which is the reference chamber is calibrated SSDL lab on a cobalt 60, you using your plane parallel chamber and cross calibrate with the reference chamber, with the pharma chamber, what the reference chamber is, the pharma chamber, which is calibrated at SSDL lab. So you cross calibrate that chamber. Your Roos chamber is cross calibrated against your primary standard calibrated chamber. So, and then you get your NDWQ cross. And normally the chamber, when you calibrate this chamber, you use the highest energy of your machine. Normally it's recommended, it should be more than your R50 of this energy, which you're using to do the cross calibration of farmer chamber to plane parallel chamber. Your the beam energy should be more than 7.5 gram per centimeter square, or maybe 7.5 centimeter. R50 should be more than that. So normally is 16 and above MeV electrons are actually have the R50 more than that. So you can use these energies to cross calibrate your Roos chamber. So this is what I said. NDWQ naught cross is a chamber calibrated factor. In our case, which we normally use it, plane parallel chamber PTW rules are like IBA. There's IBA one plane parallel one. I didn't remember what the name of it, but I think this so it's cross calibrated with the farmer chamber at electron beam energy for 20 MeV. So what it do actually, when you do the setup for the absolute measurements, what do? You get your 10 by 10 applicators. You do your 3 reading at ZRAF position of the energy. You get your 3 readings, and you have put your as a reference chamber, which is normally used to correct your beam fluctuation. If there is any beam fluctuation here, so you can correct it or normalize to that, and then you can correct it. So so the measurements you normally do, you get your raw measurements, which is electrometer reading at the ZREF, and then you correct your temperature correction factors. I asked you in the last presentation, the temperature correction factors, why we have to correct your temperature pressure for when you are actually measuring your output. The reason is because the what it do actually, these chamber are vented chamber, they are not a sealed chamber. So temperature and pressure affects the number of molecules in the cavity of the chamber, which is obeys the, the gas laws, the Charles law and Boyle's law and all these. There's a one called gas laws. PV is equal to nRT. Remember, long time back we have studied that. So basically, what it do actually, it's as you increase the pressure, what will happen, you're the you get more electron, the more, sorry, more molecules in the cavity of the chamber. And if you have a high temperature, what will happen, you pushing the distance between the molecules will be increased. So then why you get less number of electron, the air molecules in the cavity of the chamber. So then it affects your ionization basically. So that's why you have to correct it. And there's another question which I asked in the last presentation, but why you have to correct for your temperature pressure correction factor for the ambient temperatures, which is T naught and P naughts. So if anyone has an answer of it, can you please put into the comment section, so then we will discuss. Then the polarity effect, which is we discussed already. Then you have to do your recombination. If your chamber and electrometer is calibrated separately, you have to correct it for your K elect. And then your KQ Q naught included in your NDWQ cross. And if you're using like a farmer type chamber, TRS398, you can go to table 19 and you can get the table 19 for the KQQ cross Q naught. So okay, so these are the things you have to do it. Okay, next is this is a polarity effect which I discussed, temperature pressure correction and your recombination. So okay, the beam quality factor for the reference chamber. The beam quality factor is actually given in TRS398 if your chamber is cross calibrated with the farmer chamber, mean they are a plane parallel chamber which you are using for reference dosimetry is calibrated with the farmer chamber. So there is a table in TRS398. You can use this table and then you can get your KQ cross Q naught to get your, and then this is your KQQ cross field for your field chamber. This is the reference chamber. This is for your farmer chamber, and this is your parallel plate chamber. So what it do actually, this is your, it can be found in the table 4 of the TRS398, KQQ cross, when you're doing a cross calibration. So I think what I was thinking, I said in the next presentation, I think so we should plan to discuss about the cross calibration. This is I think it's a separate subject. I will discuss with you in future. Let finish this one. So I think we are pretty. What's the time now? So anyway, so then you get your NDWQ cross, which is a cross calibrated with the farmer chamber. So you get your Roos is cross calibrated with the farmer chamber. You get your NDWQ cross. So this is the basic formula. You get your dose. You have to do. This is your this first bit is the your measurement with the electrometer at the reference depth. The NDWQ cross is your calibration of your chamber, which you have cross calibrated your plane, you cross calibrated your plane parallel plate with the farmer, and this is KQQ cross. This is the X. This is what you you are measuring, because this is the energy. For example, this is the energy which you, for example, your chamber is cross calibrated at 20 MeV, but this energy is maybe like say 9 MeV. So how you want to convert back this KQQ cross? The KQQ cross is basically KQQ in with the intermediate and the KQQ cross. So what it do actually, the numerator is the beam quality factor of the given electron energy, which is the 16 MeV or 9 MeV, whatever you are doing it. Maybe is not the energy which you are which you have used for the cross calibration. The denominator is the beam quality factor for the energy used for the cross calibration. In our case, normally is 20 MeV. Um, I'm just taking as a reference. For example, if you are doing for 20 output for 20 MeV, what will be your KQQ cross? It will be 1 because KQQ int is the same as a KQQ cross. For 20 MeV, it should be 1. Okay. So SSDL calibrated parallel chambers. So what it do actually, I just said if your chamber is calibrated, what I was saying in the beginning, the part one, we talk about the if your plane parallel chamber is cross calibrated with the farmer chamber. But if you want to use the plane parallel chamber, which is calibrated at cobalt 60, so what it do actually, this is your chamber, this is the formula which you have to use it. The chamber, you can use it for this one directly, which is calibrated at cobalt 60, plane parallel chamber. The chamber calibration factor you can get from the certificate, and KQQ naught you can get from the from the beam quality factor in the TRS 398. There is a table in the uh, I didn't remember the number. I think it's I have yeah, this is the it's called table 7.3, which is give you the calibration the KQQ naught for the particular energy. If you know the R50, you can get the KQQ naught from here. But what happened? The problem is that actually the uncertainty of your measurement will be significantly changed if you use your plane parallel chamber directly calibrated at cobalt 60. So what will happen? So this is the plane parallel chamber is calibrated with the farmer with the cobalt 60, and this is the uncertainty table which is given in the TRC98, which is cross calibrated with the 16 or 20 MeV. Your plane parallel chamber is cross calibrated with the with the with the with the with the farmer chamber at 20 or 16 MeV. So what will happen if you see the plane parallel chamber? If you use the cobalt 60 calibrated, you will be get around 2.1% uncertainty, relative uncertainty in your measurements. But if you use the cross calibrated, which is the plane parallel chamber is cross calibrated to the farmer chamber, your uncertainty is reduced almost by around by 1% roughly, 0.8% something, 0.9, whatever, 6, 7%, 0.7%, sorry. So, but what happened? Okay, one question before I go to the last slide. Sorry, how can I go back? Go back. Yes. If you see on the left hand side here, you can see my mouse. So this you can see here is the relative standard deviation, but there is given a cylindrical chamber as well. You know, I mean, like a farmer chamber. You can use farmer chamber directly for beam quality of your for electrons, but the condition is your R50 should be more than 4 gram per centimeter. Mean to say the 4 centimeter at least. Your R50 should be greater or equal to 4 gram per centimeter square. But if it is less than that, you can't use your cylindrical chamber. And the reason is we have discussed the stopping power ratio, because the stopping power ratio is so significantly changed as you go to the lower energies, and it's so steep. So it is not recommended to use your farmer chamber for electron dosimetry if it is the R50 is less than 4 grams per 4 gram per centimeter square. And but if you see here on the right hand side, you can see there's also be a cylindrical chamber and the plane parallel chamber. If you have like your one chamber is calibrated, for example, I'm just what is saying is you get your chamber from SSDL, which is the farmer chamber, but this farmer chamber is cross calibrated for any particular electron energy, like 20 MeV, for example. You cross calibrated your farmer chamber for 20 MeV, and you are using it to calculate to do your reference dosimetry for your electrons. The uncertainty is almost the same if you use the plane parallel chamber, but only the one condition here, you should not more than your R50 should not more than 4 gram per centimeter square. I think you have got the point here. But the third bit which we discussed here is actually the direct beam calibration. The direct beam calibration is not available at the moment, but recently in Australia, they have started it. They are running multiple chambers, and they're trying it to establish a standard. So hopefully in next few year, maybe, I'm not sure, but at least in few years time, we should get direct beam calibration for electron beams, and we get exactly the same way which we have get it for our photons. So then it will be much easier. We don't have to do all this cross calibration and this whole complicated stuff. So then we can go directly to the plane parallel chamber, which is directly calibrated for your beam qualities for the different energies. And then you can use like they give you the fitting curves and the formula, and then you can put your R50 in it, and then you get your beam quality from there. So hopefully I have answered most of the part of it. And if you have any question, please go ahead. Thank you.
Thank you so much for very informative talk, sir. So we have a few questions in the chat box. I'll read it for you
Okay.
one by one.
Yes, please.
So the first question is, kindly explain grams per centimeter square term used in TRS 398. What that define?
That's a very good question. But basically, what it do actually is that it's not a problem. You can use as this is basically a more scientific way of saying it actually. So basically, isn't a what is saying gram per centimeter cube? What is the unit of it? Anyone
It's
can give me the
it's
idea? What is the unit of it?
so it's
Gram
gram
per
per
centimeter.
centimeter square.
It's a density, gram per cc.
Gram per centimeter cube is the density.
Yes, it's a density.
Then a gram per centimeter cube it's centimeter square. It's not a cube.
Square is area. Square is basically area, mass per unit area. Gram per
Yes.
centimeter square.
Yes.
And one is gram per 1 unit.
Yes. Very good. Very good. You are very close now. So you know what it means now.
Yes.
Self-explanatory. Just bit of brainstorming, and that's it. You will get the answer. Very good. Excellent. What is next question?
So next question is, do we need temperature pressure correction for shaded diode?
Very interesting. Shielded diode. Okay. Have used diode for reference dosimetry? If anyone used in the reference dosimetry, or maybe in vivo dosimetry?
Yeah, we use in vivo dosimetry, but not
Okay,
in a
so
reference one.
Yeah, do you correct for it for temperature and pressure?
No.
You don't correct for pressure, but you should be correcting for temperature.
Okay.
Do you know why? Because the temperature can change your depletion region. You know, it's a PN junctions. So what will happen when you temperature change, it change the conductivity in the chamber. So especially when you are using in vivo diodes, you should be correcting for your temperature. And this is the one of the acceptance testing, like a commissioning testing for the diodes materials, diode chambers. You should be checking your behavior of your diodes with the temperatures. So you should be, you use your hot water and put into the system and see how it's behaved. And you slowly increase the temperature by 1 degree or 2 degree, and you can plot it. So you should be correcting not for pressure, I agree, but for temperature, you should be correcting it. Okay, anything
Yes,
else?
sir.
But normally
So
with diode, we normally don't use it for reference dosimetry anyway. It's not recommended. Do you know why? This is the one of the exams question. So because what will happen, the the lattice of the PN junction will damage with radiations. With the time, your chamber response will change because the damage has been produced by the radiations. So that's why it's not recommended to use it, because they are not very robust chamber like a pharma chamber. They are very stable, very precise, very accurate. And the stability and the energy dependency of these chambers are really, really good. So if you use the diode chamber, they are really energy sensitive as well. So that's why there are lots of issue with that actually. Yeah, any question? Next question, please.
So next question is, why we have to apply temperature and pressure correction as a single factor rather than applying temperature correction factor and pressure correction factors separately?
Oh yes, yes. Basically, the reasoning is a gas loss, because if you see the formula is PV is equal to nRT. So your pressure change, your volume change. Sorry, if your pressure change, your number of particles in the cavity change, and if your temperature change, what will happen? It change the pressure in the cavity as well. So it's directly proportional to each other. So that's why it's not easy to separate them. So you have to, if you affect one, it's affect the others. So they found this is the best fit way to calculate your PT temperature correction factors. Hope I answered.
Okay, sir. Thank you. Sir, there are two more questions.
Yes, please.
One question is in temperature pressure correction, why do we need to have temperature corrected to 273.15 and pressure to 1013.2 hectopascal?
This
Why
is the one
can't
of
we
the
use
question.
them directly?
Yeah, this is the one of the question which I asked in my presentation. I think so the previous presentation I asked it actually, isn't it? So you remember what is the so here they say 273.2 and 273.2, and why we have to correct it for this one. I think you should be answering it actually. Very, very important. What is the Kelvin temperature? You remember the Kelvin? Have anybody heard the Kelvin temperature?
Zero degree C correspond to actually 273 Kelvin.
Yes, that's a very good answer. Very well done. So it means the physicists are very, very clever here in Pakistan. That's nice. I love it. I'm very happy with that. So very good answer. Yes. So then what will happen? 273.22 to your T naught. T naught is the chamber which is calibrated at the SSDL lab. Normally in Pakistan we use 20, I think. I remember, if I'm not wrong.
Yes, from
Yes,
20 to
and
22 degrees normally.
22 degree. Okay, so yeah, but depends. Different in Australia they use 20, and the pressure is 101.1 113.13, something like that. I don't remember exactly. So this is basically a temperature. P naught and T naught are those temperature and pressure, which is actually they used in the standard laboratories. And because in your where you are using in your clinic, maybe your temperature is not exactly, you can't control the temperature and pressure, so that's why you have to correct it, because it's changed the number of molecules in your cavity of the chamber. So that would happen, you have to correct it back what has been done in the SSDL lab. So then what will happen? You will be get the same environmental conditions which they used in the SSDL lab. Okay, next question, please.
Sir, we have Dr. Shahid from SSDL. He wants to ask a question.
Yes,
So,
please.
Dr. Shahid, you can.
Yes, Dr. Shahid, go ahead, please.
Okay, sir. In the last lecture, you said that polarity correction vector, we once take measurement for minus 300 volt. For example, if our ion chamber is being operated at minus 300 volt, then for polarity correction, we take plus 300 volt, and then we find the polarity correction factor. Do we mean that by minus 300 volt and plus 300 volt means the difference between measurement of electronic current and ionic current? Does it mean like that?
Okay. Okay. That's very good questions. So what will happen when I ask this question? I was saying that, okay, why we have to do plus
As
300
per,
and minus, yes,
sorry
please.
to interrupt you. Sorry to interrupt you. As far as I conceive, I think that minus 300 volt, we basically take electronic current, and electronic collection of electron is far more better because of their drift velocity as compared to the motion of ions or ionic drift velocity. So
Yes.
when we take plus 300 volt, then there is a slightly lag between that current value. So that's why there will be a difference, and definitely ionic current will be a slightly less than the electronic current. And then we have to basically apply the correction. This
Yes.
should be equal, but practically they are not equal.
No, exactly. The drift velocity, because the mass of the electron is much, much lesser than the
Yes.
positive ions. That makes sense?
Yes, yes.
Okay, and yeah, that's you explained beautifully. Yeah, that's the way. That's the main point. That's why you have to correct it for both for plus 300 and minus 300. What you'll do actually, for example, have you heard about when you're doing brachy in air measurement? Do you correct for polarity?
I don't have any experience of that.
Okay. Any physicists who do the brachy in air measurements?
I think mostly we didn't. I can say the reading from brachytherapy source is continuous, but the polarity correction in the photon and electron beam is like pulse. So we
Yes.
don't need it to measure K-pole in brachytherapy source.
Very good.
Sorry, I directly explain it.
No, that's all right. That's all good. All good.
Yes.
But do you remember when you get your certificate, calibration certificate, they do
Yes.
the cobalt 60. Cobalt 60 is a continuous beam, isn't it?
Yes. Yes.
And they do the polarity corrections.
Yes, that's true.
Absolutely. Isn't it? But why not for we should be doing it for like is the the iridium 192 source, brachytherapy source.
Yeah, that's good thinking actually. Yes.
So, it's it's really interesting concept. So basically,
Yeah,
normally
but
when
sorry for
brachytherapy,
the polarity correction in the ionization chamber does to know the collection efficiency in the positive voltage and negative voltage. That's effect on the reading.
yes.
So if you have a continuous source,
Yeah,
you don't need it. If you have a continuous source of radiation, you don't need it to correct it. But if you have a pulse and maybe it effect on the collection efficiency.
yep, Yeah, this is what the other guy, I think so was his name, from Prince Tech. He explained it, exactly explained this concept.
Yes.
It's based on the drift velocity of the electrons and the positrons.
Yes, and I think in the brachytherapy also the weld chamber is maybe
In
the process
brachytherapy,
is
normally what happen actually is because it's low energy, and a low
yes.
energy is so sensitive with the voltages, and yours and the other things actually is they're trying to recommend in if you read the tech talk 1273, I think, which electron the brachy one 12, anyone know, anyone remember tech talk?
No, sorry.
1273, I think 1273 is, I remember 1273 tech doc, which is actually explain why you shouldn't be doing the polarity correction, because they said it's a sensitive issue, so that it's recommended if your chamber is calibrated at SSDL lab as plus 300, you should be using plus 300. You don't use minus 300. So
Yes.
then you don't have to worry about your polarity correction factor, because you're using the same polarity which they have used it to calibrate your chamber.
Yes.
That makes sense?
Yes. Yes. Can
Okay.
I ask you another questions?
Yes, please go for it.
Sorry for I actually I have very few practical work. I have a plan to start a reference dosimetry, but I
Oh,
would
good.
like to know for the reference dosimetry of photon beams, the cylindrical farmer ionization chamber, the end of the farmer chamber should be in the axis of the beam, or the middle of the farmer should be in the axis beam, because as I see from this slide, the end of the cylindrical ionization chamber in the central axis of the beam.
Oh, no. Yeah. Sorry. It should be like this. Sorry. I can make it better. Okay. Sorry. I thanks to correct me. It should be in the middle of the effective point of measurement. Sorry. It should be in the somewhere. Where's the control point? It's here. It should be somewhere here in the middle of that.
That's I get it. Thank you. Another questions. If I use a semiflex instead farmer for the reference dosimetry, we have to change the KQ or dividing by the KQ of the farmer. If you explain this for me, I appreciate it.
Oh, okay. So yes, if your chamber is directly calibrated, I can show you. Just give me a second. There is a there's a there's a notebook. It's called
Sorry, my
PTW
question. Sorry,
PTW
I will.
absolute dosimetry. So what do you do actually if your chamber is directly calibrated at SSDL lab? So you can go to this.
Sorry, let me give you a scenario. We have a machine uncalibrated with the farmer.
Yes.
If the farmer is not available at the hospital, I have a semiflex or other chambers. Can I use it directly inside the farmer, or I have to correct it by the factor?
Okay, yes. There's a two type of the things now. If your chamber is cross calibrated with your farmer chamber, you can use it.
Yes.
Okay.
Yes,
And the other condition is you can use it if you have cobalt 60 calibration certificate for this particular chamber.
Let me tell you the scenario again. Both of the chamber, farmer and semiflex, are calibrated.
No. Can you just a quick question for you?
Yes.
Is your chamber is cross calibrated with the farmer or not?
No.
No. Okay. Is your chamber the semi-flax you have, the semi-flax which you have it is you have a calibration certificate for it?
Yes.
Okay, good. Yes, you can use it.
What about KQ?
Okay, I mean, just give me a second. I will find it for you. There is a you know PTW guide.
Yes.
If you go to PTW guide, there is a reference section in the in that one. It's called PTW absolute dosimetry. Okay.
Yes.
PTW absolute dosimetry. Okay. I think so. There's a manual there. If I find it for you, then they have all the chambers. What the PTW has it. They have their KQQ naught factors.
Yes.
Okay.
Yes. That's a good source. If you send me the link, I appreciate it.
Okay, just a second. I'm just opening it. Actually, I think so. It's loading up. So
Yes.
I'll show you on the screen. Yes, here. Okay. No, it's not this one. So there is a absolute reference dosimetry guide for PTW. I remember somewhere. PTW dosimetry solution. Okay, I think so. This is the one. It's loading up, so I can send you the link for this one. I'm pretty sure. Let me make sure that it's the right one. So they have all, even they have like a semi-flux, they have a pinpoint, they have all the other chambers. They have a beam quality factor for all the ionization chamber, but they have it there. And they are not measured one. They are done by the Monte Carlo simulations. They are the Monte Carlo simulated ones. Okay.
Yes.
Okay. So
Yes.
you can use these if you have NDWQ naught factor for your chamber from your certificate, and
Yes.
you have to correct for your, but make sure most of the IBA PTW chamber, they are not corrected for temperature and pressure. So you have to make sure the temperature correction factor is applied on it, and the polarity and recombination factor is also applied on it. Sorry, not temperature pressure, the polarity and recombination factors.
Yes.
So you want to make
Sir,
sure that.
So actually, we are running out of time, and we have questions from other participants as well. So,
Yes,
Mr.
please. You
Gafur,
can
can you
ask.
please
You can
send
ask.
your questions to the speakers directly via email?
No. They can ask me now if you have time. I can spend a few more minutes here.
Okay, sir. Okay, that's fine.
Oh yeah, this is the one. Control A. See, I can put you in a comment box. Where is the comment box? How you gonna put in comment box? Yes, please ask the question. Is anyone has any questions? I don't know. I will send you this one on the group link, so then you can find it there. I don't know where to put this. Where is the chat box?
Excuse me, sir.
Yes, please go ahead.
You said that if your ion chamber is calibrated at suppose minus 300 volt from SSDL, and you are using the same voltage for reference dosimetry at hospital or somewhere else, then there is no need to apply polarity correction factor. You said, is it?
Nah, this is for low energies. Low energies only.
For means
Like
energy of keV?
less than 300 keV.
Okay.
Low
So
energies,
it means for
because they are so sensitive. They are so sensitive. Then it's not easy to. It's not. It's not easy to measure it actually.
okay. Okay. Thank
Yeah,
you.
for
Got
high
it.
energies, you should be correcting it for it.
Thank you.
No worries.
Okay, sir. Another question is from Asad Zamir. Mr.
Yes,
Asad
Asad.
Zamir, you can ask your question.
No, thank you. I think Mr. Talat defined all the things very well, and this was really informative presentation. I will request to continue this kind of activities with other topics like small field
Yeah,
dosimetry
I
because
was
we are
discussing
so much lacking.
during the
Go on,
presentation.
Mr. Talat.
I was thinking to discuss about the cross calibration for electron, especially because electron cross calibration is not very straightforward. It's really complicated. So it's good to have like a discussion. I have already presentation ready, so it's good to talk about this.
Sir, we have a few more questions in the chat box.
Yes, please go ahead.
It's how we going to measure grams per centimeter square in clinical dosimetry.
It's basically what it do. What it do is a scientific. That's what I'm saying. It is a scientifically explaining things. But you can when you're doing your R50, you can measure your R50 in your if you see in the formula, you just put it there. R50 is, you can measure it from in the distance in centimeters, not in gram per centimeters squares. You measure in centimeters only. In reality, and use this. That makes sense.
Okay, sir. So next question is, change in temperature or pressure can change the number of molecules in the chamber, as you said
Yes.
in your explanation, because they are sealed chambers.
No, it's not. That's what I say. Is that they are vented chambers. They're not sealed chamber. Only Electa, the variant machine has a sealed chamber in their head where they do the beam monitoring. But all the dosimeter which you use for clinical is not a sealed chambers. I put
Sir,
I put the link on the chat box. You can find the